Okay, so let us continue with the Henry's law. From the Henry's law, we have a relation like this. Say, partial pressure P is equal to the Henry's constant Kh into mole fraction of the gas in the solution. So this is the mathematical formulation of Henry's law. Now let us see the graphical representation of Henry's law. In the graphical representation, we are going to draw a graph between the partial vapor pressure and the mole fraction X. We are going to draw a graph between partial vapor pressure and mole fraction. And what will be the nature of the graph obtained? That is the graphical representation of Henry's law. Okay, we have the x-axis, that is the y-axis. On the x-axis, let us plot the mole fraction X. Mole fraction X is plotted along the x-axis. The partial pressure that is plotted against the y-axis. What will be the nature of the graph obtained? The plot. You know, from the relation P is equal to Kh into X. P is directly proportional to X. P is directly proportional to X. That means when the mole fraction X increases, partial pressure also increases. So the nature of the graph will be like this. We get a straight line. We get a straight line. So when the mole fraction of the gas X is plotted against vapor pressure of the gas P, we get a straight line. It passes through origin because P is equal to Kh into X. That is similar to Y is equal to Mx. Similar to Y is equal to Mx. That is equation to a straight line passing through origin. Y is equal to Mx, equation for a straight line passing through origin. Here, the relation P is equal to Kh into X, similar to Y is equal to Mx. So we get a straight line passing through the origin. And what about the slope of this line? The slope of the line is equal to, can you say, what is the slope? Come on. Evelyn, Michael, Donna. What is the constant? That is equal to Kh. Yeah. Slope is equal to the Henry's constant Kh. So, slope is equal to Kh. And this is the graphical representation for Henry's law. So, from this, it is very clear that when vapor pressure increases, the mole fraction of the gas also increases. So that we get a straight line when the mole fraction is plotted against the vapor pressure. The slope of the straight line will be equal to the Henry's law constant Kh. Now let us see, so this is the graphical representation. Say for the examination will be asked. For the examination will be asked. You will be given a graph like this. And you will be asked to find out the slope. Or you will be asked to find out the Henry's constant. Henry's constant is the slope. You will be given a relation like this. And you will be asked to find out the Henry's constant. Henry's constant will be the slope. Kh is equal to the slope of the straight line. So this is the graphical representation of Henry's law. Now, let us see the applications of Henry's law. Some of the applications of Henry's law. Applications of Henry's law. Let us see some applications. One. See, the first one about the solubility of gases in liquids. See, our example, production of effervescent drinks. Effervescent drinks. They are produced, the soft drinks, they are, for example, soda water or soda. That is prepared by dissolving carbon dioxide under pressure. So, application one, that is a production of soft drinks. Production of soft drinks by dissolving carbon dioxide. By dissolving carbon dioxide under high pressure. High pressure. What is the use of the application of pressure? You know, when pressure increases, the mole fraction of carbon dioxide increases. In solution, it increases. That means solubility of carbon dioxide increases. So it's a direct application of Henry's law. The application of Henry's law by dissolving carbon dioxide in water under high pressure. So when high pressure is applied, the solubility of carbon dioxide increases. That is the use of applying high pressure. Henry's law application. Second one, application of Henry's law in scuba diving. Scuba diving. Say the scuba divers, they use, say, oxygen cylinder containing helium. You know, usually we inhale air, which is a mixture of, mainly a mixture of nitrogen and oxygen, mainly. Now, scuba divers, they make use of oxygen cylinders containing helium. What they do is this: they dilute air with helium. When air is diluted with helium, what happens? The percentage of nitrogen can be decreased. In the mixture, the percent of nitrogen can be decreased. In the air, we have nitrogen plus oxygen, and if it is mixed with the helium, there will be helium also. So that the percentage of nitrogen is decreased. Then, when the percentage of nitrogen is decreased, what will happen? Usually, the scuba divers will use a mixture of, say, helium 11.7% and say nitrogen 56.2% and oxygen 32.1%. That you need not remember the percentage. So air is diluted air with helium. What is the use? That is to decrease the amount of nitrogen in the mixture. If the amount of nitrogen is decreased, what is the merit of that? When the scuba divers, they go underwater due to high pressure, if only nitrogen and oxygen are there, nitrogen will dissolve in blood at a high pressure. When the scuba diver is coming out of water, The nitrogen dissolved in our blood will be forming nitrogen gas bubbles in the veins. The dissolved nitrogen will be forming gas bubbles in our veins. Production of gas bubbles, it creates severe pain, and the problem is known as bends. Due to the evolution or the formation of nitrogen gas bubbles in our veins, there will be severe pain and more healthy problems also. And that situation is called bends. If air is diluted with helium, the percentage of nitrogen can be reduced. And here helium, the solubility of helium is less compared to nitrogen. Solubility of helium is less, and therefore bends can be minimized or bends can be avoided. So the scuba divers will use air diluted with helium to avoid the problem of bends. That is, the severe pain produced due to the formation of nitrogen bubbles in our veins. So when they go underwater, due to high pressure, nitrogen will dissolve to a greater extent. And if ordinary air is used, more nitrogen will be dissolved in our blood. And when the scuba diver is coming out, dissolved nitrogen will be forming nitrogen gas bubbles in our veins, and there is severe pain known as bends. If air is diluted with helium, the amount of nitrogen can be reduced. And you compare the solubility of nitrogen and helium. If there is more amount of helium, the solubility of a helium being less than that of nitrogen, dissolved nitrogen in our blood will be less. So the problem of bends can be minimized or even prevented. The question is, say, scuba divers use oxygen cylinders or air cylinders diluted with helium. Why? The answer is, nitrogen is more soluble than helium, and if air is or oxygen is diluted with helium, the amount of nitrogen can be reduced and the dissolution of nitrogen can be reduced. And when the scuba diver is coming out, the severe pain or bends can be prevented or minimized. So another application of oil can be slow. At high pressure, more gas will be dissolving. Say underwater, that is high pressure. So more nitrogen, oxygen and helium will be dissolving. So in the place of nitrogen, if there is helium, the solubility of helium is less, and so the bends can be avoided. Okay. Then another problem, that is to avoid anoxia. So there is a situation called anoxia. What is anoxia? In the biology class, you will study this anoxia. What is that? See, the people who are living at the high altitudes, the mountain ranges, will be getting air containing less amount of oxygen. You know, at the high altitudes, the amount of air is less. Or we can say, at the high altitudes, the atmospheric pressure is low. At the high altitudes, the atmospheric pressure is low. That means the amount of air is low. That means the amount of oxygen will be less. Nitrogen and oxygen, that is air. If the pressure is low, in the atmosphere, the amount of air is low. The amount of air is low. If the amount of air is low, the amount of oxygen is also low. So, the people who are living in the high altitudes, mountain ranges, they will be absorbing air containing less amount of oxygen. So what happens? They will not get sufficient amount of oxygen for the biochemical changes. The biochemical changes will be affected by the low level of oxygen. And so what happens? There is the loss of memory power and the working capacity also. So the loss of memory power due to the low amount of oxygen, that is known as anoxia. But here, we are lucky that here the atmospheric pressure is high. There is more amount of air. There is more amount of oxygen. So normally we have this problem of anoxia. So the people who are living at the high altitudes, they suffer from the problem known as anoxia. That means the loss of thinking capacity and the loss of memory power. That is due to low amount of oxygen they are breathing. Say atmospheric pressure is low, air content is low, and so they get only less amount of oxygen into our body during breathing. And since the amount of oxygen is less, there is loss of memory power, and there will be symptoms of other weaknesses also, health problems also. And such a condition is known as anoxia. So these are the three applications of Henry's law. If the atmospheric pressure is high, the problem of anoxia can be eliminated. Second, if air is diluted with helium, the amount of nitrogen can be reduced and bends can be avoided. Then third one, in the soft drinks, effervescent drinks, carbon dioxide is dissolved under high pressure. All these are the direct applications of Henry's law. So we are saying three applications of Henry's law. One is production of soft drinks, second scuba diving, and the problem of anoxia in the case of people who are living at high altitudes. Okay. Now, let us see a binary solution of two liquids. So, binary liquid solutions. Binary liquid solutions. Binary liquid solutions. You know what is a binary solution? In a binary solution, there are only two components. There are only two components in a binary solution. That is one solute and one solvent only. If the solute and solvent both are liquids, then it is a binary liquid mixture, a binary liquid solution. For example, alcohol plus water. Alcohol plus water. Alcohol is a liquid, as you know. Water is also a liquid. So a mixture of alcohol and water is an example for binary liquid mixtures. Both are liquids, the solute and the solvent, both are liquids. And such solutions are binary liquid solutions or binary liquid mixtures. The solute and solvent both are liquids. Now let us think of the vapor pressure of such a solution. See here we have a solution, a liquid mixture. The liquid mixture, say for example, two liquids, liquid 1 and liquid 2, two liquids, or you may call them as A and B, two liquids, 1 and 2, or A and B. For example, alcohol plus water. Both these liquids are volatile. Both these are volatile. What is meant by volatility? Volatile means they are transformed into the vapor state. These are converted into the vapor state. That is what is meant by a volatile liquid. Both the liquids are, suppose both the liquids are volatile. So, above the liquid mixture, there will be vapor consisting of both the liquids, 1 and 2, A and B. So, in the vapor also, there will be two liquids, A and B. These two liquids will be there in the vapor also. We are taking a solution of two liquids. Solution of two liquids. The solute is a liquid, the solvent is also a liquid, just like alcohol plus water. And since these two liquids are volatile, they can be easily converted into the vapor state. In the vapor, there will be both the liquids, molecules of both the liquids will be there. Both A and B will be there in the vapor also. And what will be the proportion of A and B or 1 and 2 in the vapor? The proportion of A and B or the proportion of 1 and B, that depends on the volatility of the two liquids. If one liquid is more volatile, that means boiling point is low. That is why it is converted into the vapor state easily. So, more volatile liquids will be easily transformed into the vapor state. So, in the vapor mixture, there will be more amount of the more volatile liquid. The vapor mixture, the amount of the components will be, the more volatile liquid will be more, molecules of more volatile liquids will be more in the vapor. Definitely in the vapor, both the liquids will be there. Liquids means molecules of both the liquids, vapor mixture. That is also a mixture. But in the vapor, there will be molecules of both the liquids, which will be having a higher proportion. The more volatile liquid, that means the liquid with a lower boiling point, that will be vaporized more. So the proportion of the more volatile liquid will be more in the vapor mixture. In the vapor mixture, there will be the more volatile liquid. Both will be there, but the amount of the more volatile liquid will be more in the vapor mixture. Now, let us see the pressure due to the various components. The pressure due to vapor above the surface of a liquid is called the vapor pressure. Do you remember? We have studied in the +1. In the +1, we have studied that. So pressure, the pressure due to vapor, pressure due to vapor above the surface of a liquid, surface of a liquid, that is called the vapor pressure. That is called vapor pressure. So vapor pressure of a liquid is the pressure due to the pressure exerted by vapor sealed above the surface of a liquid. The vapor above the surface of a liquid exerts a pressure, and the pressure due to vapor above the surface of a liquid is called vapor pressure. Okay. Now, if both the liquids are volatile, so the vapor is also a mixture of both the liquids. The vapor is also a mixture of the liquids. So each vapor will be exerting a pressure. There will be vapor of A and the vapor of B also. The pressure due to each component is called partial vapor pressure. It is a partial vapor pressure. So it is the pressure exerted by each vapor. That is called a partial vapor pressure. Suppose we have two liquids, 1 and 2. The partial vapor pressure, let it be P1 of A. Component 1 is equal to P1. Partial vapor pressure due to component 2 is equal to P2. Now you take the sum of the partial vapor pressures, and that is equal to P total, P total. So the total vapor pressure will be the sum of the partial vapor pressures of each component. Say we have two liquids, 1 and 2. The partial vapor pressure of component 1 is equal to P1. Partial vapor pressure of component 2 is equal to 2. Now total vapor pressure of the mixture, the vapor mixture, Pt, is equal to the sum of all the vapor pressures, that is P1 plus P2. So P total is equal to P1 plus P2, where P1 and P2 are the partial vapor pressures of all the components 1 and 2. Let us come back to the vapor pressure and the partial vapor pressure again. Okay. What is meant by vapor pressure? I repeat, the pressure exerted by or the pressure due to the vapor sealed above a liquid, that is called the vapor pressure. If we have a liquid mixture, in the vapor there will be molecules of both the liquids. So the vapor is also a mixture of the components. For example, 1 and 2. The pressure due to each component is called the partial vapor pressure of the component. If P1 is equal to partial vapor pressure of component 1 and P2 is equal to partial vapor pressure of component 2, then total vapor pressure is equal to Pt is equal to P total is equal to P1 plus P2. Is it clear now? Alright. May I proceed? Okay. So P total is equal to P1 plus P2. Sum of the partial vapor pressures of the various components. Okay. Now let us see a law that is known as Raoult's law. That's called Raoult's law. So let us go to the Reynolds law. Reynolds law. And what is Reynolds law? Reynolds law is a relation between partial vapor pressure of a volatile component and mole fraction of the component in the solution. The partial vapor pressure of the component and the mole fraction of the component in the solution. Is it clear? Relation between partial vapor pressure of a component and mole fraction of the component in the solution, and that relation is known as Reynolds law. According to Reynolds law, say P1 is equal to partial vapor pressure of a component 1, then P2 is equal to partial vapor pressure of a component 2. Then according to Reynolds law, P1 is proportional to x1 and P2 proportional to x2. P1 proportional to x1, P2 proportional to x2. Or we can write P1 is equal to a constant P10 into x1. P10 into x1. We get a relation like this. Similarly, P2 is equal to a constant P20 into x2. P2 is equal to P20 into x2, and that is the mathematical formulation of Reynolds law. According to Reynolds law, the partial vapor pressure of a volatile component is directly proportional to mole fraction of the component in the solution. Please don't misunderstand. In the solution, mole fraction of the component in the solution. If P1 and P2 are the partial vapor pressures of components 1 and 2, and x1 and x2 are the mole fractions of 1 and 2 in the solution, then according to Reynolds law, P1 proportional to x1, P2 proportional to x2, or P1 is equal to P10 into x1, then P2 is equal to P20 into x2, where x1 is mole fraction of the component 1 in the solution, and x2 is the mole fraction of component 2 in the solution. You know, x1 plus x2 is equal to 1. That you have studied already. So, if x1 is known, then x2 is equal to therefore, x1 plus x2 is equal to 1. So, if x1 is known to us, if x1 is known to us, then x2 can be obtained like this. x2 is equal to 1 minus x1. Or we can write x1 is equal to 1 minus x2. So, remember this one only. x1 plus x2 is equal to 1. Sum is equal to 1. So we get the relation P1 is equal to P10 into x1, P2 is equal to P20 into x2. Now what is P10 and what is P20? P10 is the vapor pressure due to pure component 1. If there is only the component 1, if there is only the component 1, that is not a solution at all. That is not a solution. There is only one liquid. There is only one liquid. Liquid number 1. Similarly, liquid number 2, there is only one liquid. So, P1 is equal to pressure due to the pure component 1. P10 is equal to pressure due to the component, pure component. There is only one component, pure component 1. Pure component 1. Similarly, P20 is equal to pressure due to pressure exerted by or pressure due to pure component 2. Pure component 2. That means these are not solutions. Only component 1 or component 2, only these two are there. And therefore, that value will be a constant. P10 is a constant. P20 is a constant at constant temperature. The proportionality constant, P10 is a constant. P20 is another constant at constant temperature. So, P1 is equal to P10 into X1, where P10 is equal to pressure due to pure component 1. Then P2 is equal to P20 into X2, P20 into X2, where P20 is equal to pressure due to pure component 2. So these two equations are derived from Raoult's law. Let me go back to Raoult's law. Raoult's law. According to Raoult's law, the partial vapor pressure of a volatile component is directly proportional to mole fraction of the component in the solution. So, P1 proportional to X1, or P1 is equal to P10 into X1. P10 is equal to pressure due to pure component 1. Similarly, P2 proportional to X2. Therefore, P2 is equal to P20 into X2, where P20 is equal to pressure due to pure component 2. So we have got two relations from the Raoult's law. Here, both the components, component 1 and component 2, both these components are volatile components. Both are volatile components. So, partial vapor pressure directly proportional to mole fraction in the solution state. So, P1 is equal to P10 into X1, P2 is equal to P20 into X2. Okay, now let me think of the vapor pressure of the components in. Let me write the Raoult's law like this. According to Raoult's law, P1 is equal to P10 into X1. Similarly, P2 is equal to P20 into X2, where P1 and P2 are the partial vapor pressures of components 1 and 2. Okay, now let us try to draw a graph between the partial vapor pressure and the mole fraction. Partial vapor pressure and the mole fraction. Water? Okay, oh sorry. Okay, so we just remember up to this. So inform that the time is over. So according to Raoult's law, partial vapor pressure of a component is directly proportional to mole fraction of the component in the solution. So P1 is equal to P10 into X1, P2 is equal to P20 into X2, where P10 and P20 are the pressures, the vapor pressures due to the pure components 1 and 2. Okay, so remember these two equations for the next day. we can draw the graph the next day. It is time, let me stop now. Very good. Okay, it's all right. It's all right.